Hello everyone, welcome to today's presentation sponsored by Seal Aftermarket Products. Let me play you a short video from Seal Aftermarket.
Seal Aftermarket Products engineers and manufactures Toledo Transkit, the most trusted and complete kits in the industry for 25 years. Toledo Transkit gives you more critical components, more OE components, like premium seals and gaskets, more design enhancements, patented components, and all the little extras you won't find elsewhere. At Seal Aftermarket Products, we don't just make kits, we make kits better. Toledo Transkit is the #1 choice of installers because of all the intensive research and development that goes into each component in every kit. Like re-engineered valve body gaskets, preventing EPC damage by eliminating the shredding you get from original equipment. Plus, all of the extra essentials that are included, like spring and screen filters that should be changed at overhaul. Toledo Transkit even includes loose valve body gaskets that fit all 19 bonded separator plates. When servicing Honda and ATRA transmissions, shaft nuts are quite often damaged during removal. Toledo Transkit provides all the main shaft, secondary shaft, and counter shaft nuts, so you don't have to try to reuse the originals or pay extra for them at the dealer. Honda Acura kits also include valve body screen filters, pressure tap washers, and other important components like bolt locks, roll pins, and pistons. What you get is a complete kit with great fit and no wasted time or worry about ordering extra parts. If you want the best sealing transmission kit in the industry, ask for Toledo Transkit by name.
Okay, if you have any questions or comments, please send your emails to webinars@atra.com. If you have any questions during the webinar, please feel free to go ahead and text them to me, and I will answer those the best that I can. This is the schedule for the rest of the year for the free webinars that we're having. August 18 and 19th, we'll be doing the U660E and some comparisons with the U760E internal components. This is the dates for the ATRA Expo in Las Vegas again this year. We'll be at the Rio, and it's October 29th through November 1st, Halloween weekend. This is the schedule for the rest of the year in the States for the ATRA seminars. This Saturday will be Albuquerque, New Mexico. Along with the door prizes given away by the vendors, this year ATRA has a few door prizes of our own. One of them is a 1-month free tech service. If you're already a member of ATRA, we'll just take a month off your bill. And then we're also giving away last year's Expo book with almost 800 pages of tech in it, as well as one management tech seminars registration for free. Just have to get your travel expenses there and your expenses while you're staying, but the management seminars are on us. And then last but not least, we're giving one free Expo package that covers both the management and the tech seminars. You go to either one. And as well with that, we're going to give away a 4-night stay at the Rio. So you just have to get your expenses, traveling expenses, to get to and from Vegas. Today's presentation, we're going to be talking about the internal components, mostly on the 8L90. We've already covered the introduction a few weeks back. This is something new, the ratios for the 2016 models. That's the 3 different Cadillac models you see here. And there'll be an 8L45 as well as an 8L90 going by the engine size. And you can see the 2 different ratios for those 2 different engines. A little update on the solenoids. The solenoid names and locations haven't changed, but just another way of identifying what solenoid goes where. As you can see in the casting of the valve body, there's embossed letters. and these letters match to the solenoid. So if you mark the solenoids before you remove them, you'll know exactly where they go because it's embossed in the case. This chart that explains which solenoid goes where, describes the solenoid, gives you the resistance value for it. And what you see at the bottom in the red square, on most training manuals or factory manuals, that mistake is, that information is mistaken. It's not correct. We found that in the manual you'll find the G will be at the bottom and the H at the top, and that's not right. It's correct as you see it here on your in your handout material. A little bit of an update also to the solenoid apply chart compared to the one we did on the intro. The different names for the solenoids have changed slightly, but the chart is still the same as far as when the solenoids are working. So it's not an electrical chart. On just means the solenoid is working, and off would be the solenoid is not working. So if you've got a normally low solenoid like we see here, obviously if the solenoid is off, it's actually going to have no pressure. The solenoid is normally high. When it's off, it's going to have pressure. So as you can see here, when we turn it on, it actually lowers pressure on that circuit. And this is the solenoid function. We have two 3-port on-off shift solenoids that are normally closed. And the way those work is you have supply pressure or actuator feed limit oil coming into the solenoid here. And when the solenoid is off, it's closed. So any pressure that's in the circuit will actually exhaust out through the back of the solenoid. So even though it's normally closed, it's not holding pressure, it just blocks the circuit from getting any feed oil. Now when the solenoid is turned on, obviously the exhaust is blocked, and now the actuator feed limit oil can go to the control circuit. Okay, there's 4 normally high pressure solenoids, and this is kind of how they work. With actuator feed oil coming into the solenoid between these 2 O-rings, and the solenoid will regulate that pressure. It'll regulate the pressure to the accumulator to that solenoid, and also it's going to regulate the pressure going to the valve. The accumulator is there to take the pulse out of the signal to smooth out the signal from the solenoid. The valve will stroke to the left, and then we'll have oil pressure going to our clutch. We turn the solenoid on. Basically, it's going to block off the pressure from the actuator feed, and with no pressure going to the valve stays stroked to the right, and our clutch pressure will just basically drain. And there's 3 normally low pressure solenoids. As you can see here on the right, they're using line pressure to go to the front of the solenoid. When the solenoid is off, there's no pressure allowed into the circuit, and the clutch stays released. We turn the solenoid on. Now line pressure can be regulated through the solenoid. As you can see here, it's going to the solenoid accumulator, and then it actually strokes the valve to the left, and we have clutch oil going to our clutches. This is the external case connector you're looking at here. We identified all the pins, and you have the chart there on the left to check all the solenoids and speed sensors inside the transmission right there from the outside. This is the internal harness that's on top of the valve body, and we give you the pin ID for the harness coming in from the case connector right there on your left, and then the harness that goes to all the solenoids in the upper right. As you can see, the temp sensor is part of the main harness, and it's a typical thermistor type temperature sensor. We identified all the pins as well as what circuit it goes to and the color of the wiring going to that circuit. And the speed sensors have a separate connection that you can see here on the bottom left. You can actually unplug them from the main harness going out to the case connector. and we identify the pins for that. And we also identify the pins to the harness going to the sensors itself. These are all 2-wire Hall effect speed sensors. There's 3 of them in all. Now the way the Hall effects work, this is a simple diagram of basically how they work. You can see the exciter wheel goes by the magnet at the tip of the sensor. The top one is a 3-wire Hall effect, so it's supplied voltage anywhere from 8 to 12 volts. It's grounded back at the TCM or PCM, and then you can see this signal will be pulsed to ground as the wheel spins past the magnet. Now a 2-wire Hall effect, same similar setup. Inside there's a capacitor, and your supply voltage will go through, and that'll be pulsed to ground, and you can see there's a resistance in the circuit. So that's how the 2-wire Hall effect works. There'll still be a square wave signal, just like you would see on a 3-wire. Now if you have them on the bench and you're not sure whether the 2-wire sensor you have is an AC pulse generator, which produces AC voltage, they're considered a permanent magnet. Take your meter out, set it on diode test, and as you can see on the left, this is a regular 2-wire pulse generator, produces AC volts. So if you put your leads on each pin, you'll see a voltage signal. That'll vary from different models. Then if you switch your leads like you see on the right, the voltage should stay the same. That would simply tell us that we have a typical pulse generator AC voltage type speed sensor. Now the one on the right is a 2-wire Hall effect. We have the meter on the same setting on the diode test. Now we set our meter leads onto the sensor pins, and we should get a voltage reading. Now if we take the leads and swap them like we're doing here on the right, the voltage should change. That would tell you that you have a 2-wire Hall effect. Again, the voltage readings that you see here on this test could obviously be different on different models. So this is where the 3 speed sensors actually align to the components inside the case. As you can see on the right, that's the input speed sensor, and there's an exciter wheel that's right on the drum of the 13567 clutch. Also, what I'm showing you in that diagram there is that I noticed that where each one of the sensors bolts down, there was a rubber grommet that went to the bolt. So I want to make sure we don't lose those and those go back in place. Now, the output speed sensor is pretty typical. You can see it's monitoring the ring of teeth on the output carrier. But the sensor in the middle, the GM refers to this as a clutch input speed sensor. They don't call it intermediate. More of us are used to hearing it being called intermediate, but that's what GM calls that. And that's actually monitoring the ring of teeth on the reaction carrier. And in the bottom left, you can see where they both bolt up. And that's where they bolt up into the case and monitor those 2 rings. This is the internal mode switch connector view. We give you the actual connector pin ID on the sensor itself and on the harness going down into the sensor. They also give you a chart in your handout if you want to monitor that voltage on your scan tool data, or if you actually wanted to back probe the pins and move the selector through the different detents and monitor the voltage yourself. Okay, this is the start surge accumulator. This is where it would be bolt up if this had one. From the information I've seen from General Motors, the start feature is going to start in 2016. Now, it's normal to drop the pan on one of these and you're going to see that empty spot like something belongs there. The oil is controlled to it whether it has the surge accumulator or not, so it's not going to cause any leaks. This is what the surge accumulator looks like. Obviously, we have an auxiliary fluid accumulator solenoid. This is going to control the fill and release of this oil. And you can see there's a bleeder valve on there also. Got 2 large springs inside. Now when the engine's off, the surge accumulator stores line pressure. Now when the driver lets his foot up off the brake and goes to hit the gas pedal, the surge accumulator solenoid, it now opens, sending all that stored oil pressure to the two different paths. The first path that actually opens a check ball number 20 and seats check ball number 9. This prevents the surge oil from going to the pump. Now this oil goes through the 13567 regulator valve to apply the 13567 clutch, and it also goes through the 1278 reverse regulator valve to apply the 1278 reverse clutch. The second path is the surge oil goes directly to the 12345 reverse clutch, and these clutches provide first gear in preparation when the engine's restarted. This is the component layout. You can see we have our 4 planetaries all aligned in the back of the case, as well as our 2 brake clutches are in the back of the case. All of our driving clutches are up front. It's a one-piece case. It'll be more rigid, more solid. And the reasoning for the 3 driving clutches up front, from information I received from the General Motors engineers, is a shorter path for the valve body to supply oil to those shifting clutches. A little bit closer look at the internal parts is the Planetary Assemblies. And what we have, as you can see, we have the output shaft to the right, and spline to that is the output sun gear. And that will go up into the output carrier. And on top of that, we will have the reaction carrier to the right. I just show the carrier with the planet removed, and you get a better look at the ring gear. And then, of course, then we have the 12345 reverse clutch hub, which is all part of the reaction internal gear. Then you have the reaction sun gear and the input sun gear that's actually on the 1278 reverse clutch hub. Once that's all put together, it'll look like that on the left, with the snap ring holding everything in place. With all these components together, and we would load next the input carrier that you see here, and it would go on top of that. And then we would have the direct overdrive sun gear. I flipped it over to the right so you can see the ring gear on the bottom. And then we'd have the direct overdrive carrier, and then the last piece would be the direct overdrive internal ring gear, which is the hub to the 23468 clutch. So it just gives you a general layout. This is what it would look like with everything assembled. And you can see all the different carriers. We have all 4 carriers there. Now the reason for putting this information together this way is because I wanted to show the power flow in the next few slides. I like using power flows when I have to diagnose any type of a noise. Power flow charts, as well as looking at the drivetrain, seeing what's driven, what's being held, and actually what the driving component is. It's a lot easier to find noises, especially when the noise changes during a shift. So this is the power flow in reverse. You can see the E clutch is driving, the A and B clutch are holding. And down below we have all the different carriers as far as the ring gear is driven. It's turning counterclockwise. You can see the planet's turning with it counterclockwise. They're all being driven in that direction, and which drives the sun gear in the opposite direction. The ratio in reverse is 3.818 to 1. Now this is the power flow for first gears. We still have our A and B clutch holding. Now we have the C clutch driving. Our ratio is 4.560 to 1. And as you can see on takeoff, the direct overdrive carrier ring gear is not being held. It's not doing anything. There's no load on it. So when we shift to second gear, the D clutch is now driving. The A and B clutch is still holding. Our ratio changes now to 2.971 to 1. carriers change, whether it's being held or driven, if our noise changes here, that's the one component we need to look at. As you can see, we go from one to the other, and you can see the changes. Now we're in third gear. The ratio is 2.075 to 1. We only have the B brake clutch holding. The C and D clutch are driving. Notice the two sun gears on the input and reaction carrier are now not carrying any load. This is the first place to look if we have a noise that goes away in third. Now in fourth gear, the E and D clutch are driving, B clutch is still holding. And we have a ratio of 1.688 to 1. Again, using this information would be great for trying to chase a noise. Now you can see some parts have swapped from driving to driven. The C and E clutch is now on. We're at a 1.270 to 1. We're still under driving. And now we go to sixth gear, which is a 1-to-1 ratio. Notice the reaction carrier. No components in the reaction carrier are carrying any load or producing any torque. This is also fail-safe for this transmission. So now we're at a 1-to-1. When we go to seventh gear, we're overdriven at 0.845 to 1. And you can see the reaction carrier in sun gear comes back into play. So if our noise wasn't there and goes away in sixth, comes back in seventh, this is the first place to look. And then we have eighth gear. Now the A clutch, brake clutch is holding, E and D clutch are driving, and you can see our ratio now is overdriven at 0.652 to 1. So take time, look at the material. If you happen to be dealing with a problem with a certain shift that's giving you noise, this should help you out. I want to talk a little bit about the clutch clearances. These are the clutch clearances using the factory method. A few webinars back, I did a webinar on the ZF8, and I received an email and a phone call saying that my alternative method of checking the clutch packs wasn't accurate enough. So I wrote an article just recently, should be out in the next couple months, and we'll go through my alternate method, and I'll show you some of my results, or I'll tell you about some of my results, doing it my way and doing it according to the factory. Now, as you can see here, you have to buy some equipment to do it the factory way. They want you to compress the clutches as much as 80 pounds of force. They want the clutch pretty much flattened out. And you can see the tool has a bracket that puts it on the bell housing for the clutches in the case. And then on the right, you can see the different clutch packs, and the driving clutches can be used by this other tool, can be checked this way. You have all the numbers for the tools. These are OE numbers. This is the adjustable clutch spring compression tool. It can be adjusted to different heights. And this is they're giving you 3 places to compress the clutch assembly so that you can check your measurements. There's the gauge that goes to it, so you can monitor the force of pressure you're putting down on the clutch. And they also have a spacer tool you see on the right, so you won't have to make less adjustments to that other tool or a shorter clutch pack. Also, there's an air check tool that they want you to air check the clutch and check the adjustment. That's the numbers for the air check tool. According to GM, they have replacement O-rings available for it. I don't have any part numbers for the O-rings. All I have is the part numbers for the tools themselves. Now this is the spring compression bridge. You have that part number in your book. That's the one that goes across the case, and we do the 2 clutch packs down inside the case. And then obviously we need a dial indicator that can clamp to the case. This tool really hasn't anything to do with clutch end plate. It's just a loading tool. I found the information for this, just added it to the webinar. Now the unit that we took apart, we removed the output shaft and the planets from the back of the case. Obviously, if we went back together that way, if we put that section together first, then we would have to have something to hold the output shaft in place while we were loading the rest of the transmission. Now, these tools, I have no prices for them. I don't know what the prices are. You can either price them out, or obviously using this information, you can make tools of your own to use in place of these. Now, this is my alternate method. Instead of trying to compress the clutch pack inside the case, what I was doing is I removed the wave plate. Now I'll assemble everything into the case. I'll check my end plate, subtract the thickness of the wave plate, and that gets me pretty close to what the factory specs are. Now the factory specs for this clutch is 37 to 72 thousandths. That's quite a big difference between the two. There's plenty of room in there. Now when I did this without the plate, and we took our measurements, then when I compressed the clutch pack, I was off. The maximum I was off is about 2 thousandths. So even though the spring is not completely compressed under 80 psi, we actually compressed it all the way down, and we got a difference of about 1.5 to 2 thousandths on different clutch packs. We checked it on this unit. We also checked it on the ZF8 unit and several others. Now I've seen some pressures in factory manuals saying to compress the clutch pack to, and it actually read in the manual, I don't know if it was a misprint or not, but it read 1,000 pounds. Now, not that we're going to do that, but obviously what they were trying to do is completely flatten out the wave spring. So that's my alternate method. If you want to try using it for yourself, if not, that's fine. You can do it whichever way you want. You can use it the actual 80 pounds of force and check your end plate that way. So we got the clutches in there, the wave plate, made our measurement, and subtracted the thickness of the wave plate from our total measurement. And we did the same thing here with this clutch, the 1278 reverse. This one gives you 10 thousandths leeway, so if you're off about 2 thousandths, you'll be closer to being tighter than loose. When we went to assemble the clutches into the case, what I'm pointing at with the screwdriver is the notch in the case where this tab has to align to. So get that down in there and put the snap rings in, had everything assembled. We flipped the unit around to the back, and we did our end plate check that way. Again, we subtracted the thickness of the wave plate from our total clearance, and we were right within specs there. Now for one of the driving clutches, the 45678 reverse, you can see we've got about 26 thousandths of clearance that they're looking for. So again, 1.5 to 2 thousandths, not going to be that critical here. We check our end plate the same way. Take the wave plate out, drop everything in place. Now, while we were doing this on the bench, I made this mistake, so I took a picture of it. This has a blind spot or a blind spline in the drum. This is the incorrect way to put the snap ring in. This probably would have lasted about 1 or 2 shifts, and then the snap ring would have came out and we would have had a problem with the clutch pack. On the right, you can see it's just like a 6L80. There's a blind spline that you have to put the opening of the snap ring there. Now for the bottom clutch, the 23468 clutch, this one here is about 26 thousandths also, between the 61 and the 87. Again, we did our alternate method. We stacked our clutches down into the drum, and of course we made sure we had our snap ring in the right place. And then the last clutch we did was the 13567 clutch. Now there's 2 different measurements here. They have a 4 clutch drum that the clearance should be between 72 to 91 thousandths. And if you have a 5 clutch drum, They want it to be a little bit tighter. They want it to like 59 to 83 thousandths. Again, to me, I would think more clutches, more clearance, but as you can see here, for some reason, this is what the factory manual had for specifications. There's no weight plate in this drum. There really was no need to compress it. You can check and see if there's any waviness to the clutch. I didn't actually check it on this one, but I did put some pressure down on it to see if it was spongy in any way. Now, when we got to the end of the unit and we wanted to do some end plate checks here, in the factory manual there was no one check that you could use. They showed, now this is the factory method. You can use an H gauge if you have one. But they want you to take a flat edge, put it across the mating surface where the front support would be bolted down to the case, and take a measurement and, of course, subtract the thickness of the straight edge. And that's when you have the 4, 5, 6, 7, 8 reverse clutch in place. They want you to take a measurement there, make sure that everything is assembled correctly. You should have 2.472 thousandths clearance or end play. And then they want you to load the last drum, the 1, 3, 5, 6, 7 clutch, and again take a flat edge and make a measurement. It should be about 416 thousandths. That's after you subtract the thickness of the straight edge. Myself, I would probably just use an H gauge, make my measurement, flip it over, check my clearance, make sure that everything is aligned correctly. We added the check ball location and function to this webinar, and you can see we have the hydraulics shown here for you for each check ball and what clutch it controls. Now on this slide, this page of your handout, you'll see this is where the number 9 and the number 20 large check ball would be if this had the surge accumulator. And this is the last set of check balls that goes into the valve body here. And we identify each circuit that's being controlled through these check balls. And then we have the accumulator function also. You'll notice that 6 out of the 7 accumulators are for shift field. They're controlling the pulse of oil from the solenoids. They're trying to smooth that out. And then we have the S6, which is actually controlling the signal from the line pressure solenoid. Then we have our case air checks. This is how we discovered that the information in the factory manual or the factory training book stated that the bottom fitting was the line pressure and the upper one was the 1, 2, 3, 4, 5 reverse brake clutch. Well, obviously when we checked it here, we could see that if we put pressure in the upper one, it didn't apply the clutch. So some of that information in the training manual was off also. We did the same thing with the cooler flow. We checked that to see which one was from the cooler and to the cooler. So here you can do some air checks to each clutch with the transmission completely assembled. There's your to and from cooler, and then your identification for your taps. The line pressure specs can be found in the previous webinar we did, the introduction webinar. And I have the service information covered in the earlier webinar also. I didn't have a good picture of where the drain and the fill level plug was located. So I just put that in here at the end of this webinar. And that's it, today's presentation. I want to thank you all for attending. If you have any questions at this point, please click on the little hand icon by your name so I don't close the webinar out too soon.